Okay, so we are very happy today to have Professor César Galindo, who is a professor of mathematics at Universidad de Los Andes, Bogotá, Colombia. His research interests focus on the organization theory of quantum groups and fusion categories, with an emphasis on application to quantum computing. Today, we will talk about categorical Fermionic action and minimal modular extension. Let's start.
Thank you very much for the introduction and really also for the invitation to come here. I'm really happy. It's my first time in China, but also I'm very impressed everything and for the hospitality. I'm very happy to share something that I have been working on. Okay, so I want to, this is the outline of the talk. I want to start directly showing you what is the problem and the solution that I wanted to present without too much definitions. Just that you know exactly what it is about. And then in the second part, I will describe with some preliminaries and concrete definition what is the formal problem that I want to have. And this problem that I want to present, that is the obstruction theory of minimal molar extensions, needs to be divided naturally in two parts. So in this part, I will describe when the solution in one particular case, and after that, the solution in the other particular case, and the conclusion. That's the plan of the talk. And please interrupt me at any moment, any question. I'm really happy to have a discussion. Okay, so what is the problem that I want to solve? This is a problem that has kind of interesting story. It came from a paper of Michael Müger in 2003, when he has a conjecture that those days was known as the Müger conjecture, and said that every existing minimal molar extension, that later I will explain exactly what it means, but given a braided category, the idea is to have to include it, to embed it in a molar category of the minimal possible dimension. Müger found some bounds, and he asked naturally if the bound is always possible or not. And there is an unpublished notes by Greenfield around, I don't know exactly the time, but around 2009, 2008, I don't know exactly, when a counterexample appeared. So Müger's conjecture was false. It was very interesting because at the moment it was very interesting. And then Liang, Kong, and Xiao Wen, in this paper in 2017, they proved that if you could fix a braided category and consider the set of equivalent classes of this minimal molar extension, this is in a natural way a transitive, free and transitive group, a free and transitive set. So it's a torsor over some particular abelian group that I don't want to explain at this moment, but there is, I mean, the set of all molar extension is a torsor, or possibly C empty, because we know that there are some molar categories that doesn't admit. So it's a torsor over some particular group canonically associated with the braided category. To be honest, at this moment is when my result appears, but I will put the other part of the story that is quite important. Well, not It's a result of Theo Johnson-Fay and David Hoyta that says that, okay, the conjecture is false, but in the case that the Müger center is a very particular important case, that the Müger center is the category of supervector space always exists. And this particular case, there is 16 minimal molar extension, and this was like a open problem for a long time, a very difficult problem at the moment. So this was a breakthrough. I mean, it was a very important result, I can say. This is also quite interesting. And so what we did, as I said, the idea is that this is an empty torso. So the natural question is when this is an empty set, because once you know that this is not empty, the problem translates just to compute this abelian group. So the real problem now is to know when this group is, when this set is empty or not. What did happen now?
Oh, maybe move the mouse back down for you.
Okay.
Go back.
Yeah. So our main result is to provide necessary and sufficient conditions for the system of minimal molar extension via cohomological obstruction. So it's a group cohomological thing and procedure in order to know when molar extension exists or not. And as Johnson, Freyd, and Reuter emphasized in his paper, using our result, Liang-Tong-Ven result, and Johnson-Freyd result, we think that this closes the program of classification of minimal non-degenerate extensions or minimal molar extensions of braided fusion categories. This is what I want to present today, is how this obstruction theory looks like. Yeah. So that's our main result. And that's why we believe it is important. Okay, so first, what is a fusion category? Well, a fusion category is a semi-simple, rigid tensor category. Typical example, category representations of a group, but there are many others very important, such that there are finitely many isomorphism classes, finite dimensional morphism space, and the unit object is simple. When you have a fusion category, there is in particular invariant that is called the Perron-Frobenius dimension. Here I won't say exactly what is, but for example, in the case that this is the category representation of a group corresponds to the order of the group, or if it is the category representation of a Hopf algebra that corresponds to the dimension of the Hopf algebra. Typically, in many cases, this is an integer, but it doesn't have to be an integer. Either, for example, categories associated with quantum groups, molar categories associated with quantum groups, those are examples of things when this is not an integer. Always is an algebraic integer, but not an integer. And as I said, the typical examples are the category of complex representations of a finite group, and this one that will play an important role in many examples, at least take a finite group, then consider the category of vector graded spaces, and this omega is a free cocycle. And using this free cocycle, you can twist the associativity constraint. This is another typical example. Those are called pointed fusion categories, and all possible pointed fusion categories can be described in this way. And of course, the other big family of important examples is the semi-simplification of tilted models of a quantum group at root of the union. But here, I am interested in fusion category with an additional structure that is a braid or braiding. And a braiding will be a natural isomorphism between X tensor Y and Y tensor X that satisfies some axioms that is usually they are called the hexagon axioms. At this moment, doesn't matter too much the axioms, but the important part is that you have the natural isomorphism. It plays a very important role in all story. I will tell you. And look that in this case, there are there is one category canonical associated that some people call the Müger center or the transparent of the category of transparent objects. And it corresponds to those objects in the category that for any other possible object, when you apply the double braid, then it's when you do this and after that you this, you obtain this. This is when you consider this category, this is the Müger center, and there are two extreme cases. One is when the Müger center is everything, and in this case, what you are doing is adding an additional condition to the braid, and this is called a symmetric fusion category. That's the one extreme case. And the other extreme case is when only the unit object is, and this is called non-degenerate. And this is very close to the notion of modular tensor category. Modular means that in addition to this, you have a ribbon structure. But again, I don't need the ribbon structure in order to describe. So for that reason, I want to present this part, but it's just. So the point is that you have two extreme cases. The symmetric one, that this Müger center is everything, and the non-degenerate case when the Müger center is the smallest possible count. And one important thing that I will use is that symmetric fusion categories are completely classified, and they are basically category of representations of a group. There is one case that is called the Tannakian case, that is when the category has a fiber counter, and this is called, in this case, is the typical category representation of a group with the ordinary symmetry. And the other case is the case of super-Tannakian, that is, as a category, as a fusion category, is exactly the same as this one. But now you have a central element of order 2. So if you pick, for example, any simple object, this central element of order 2 acts as the identity or minus the identity. So that's defined like a grading over the set of simple objects, and then you define the braiding similar to the previous braiding, but now you use this grading. So if the category, I mean, if Z acts as -1 over the object S, then you use that. So this power is 1 or -1, depending on if Z acts as 1 or -1. So it's 0 or 1, depending on what. Yeah. Yeah. And this is a typical example, and it's the category of super-vector spaces. Yeah. So if you forget about this part, the category of representation of the cyclic group of order 2 only have two simple objects, the trivial representation and the other one. So any object here can be seen as a vector space graded over, let's say, 0 and 1. But the point now is that the grading, because it's this one, depends of if the vector space is even or odd. So it depends of the grading over this vector space and satisfy this same symmetry. Okay, now what exactly is this notion of modular extension? I decided to take directly some pictures from the paper of Michael Müger, because it's nice to see the original, let's say, definition and how he did it. He proved the following proposition. If you have a unitary, he was working in the case of unitary, but now it's known that you don't need unitarity, and even you don't need to be modular, only you need to be non-degenerate. That's the only thing that you need. But the original was in this case. So if you have a unitary modular category, and you have inside some fusion subcategory, then the dimension of the category Z, it's bigger or equal than the dimension of this subcategory times the dimension of the Müger center. Always is bound by it. Yeah. Again, now we know that this kind of result is true without unitary modular, and then instead of dimension, the quantum dimension, you use the Frobenius-Perron dimension. Yes. And again, this is taken from this paper of Michael Müger. This is the Müger's conjecture. He said that he believed in that moment that always exists this inclusion, so this bigger molar category that you can get the bound. Yeah, what's this? So this is the definition of a minimal molar extension. So it's a bigger category that contains your original category such that the dimension, I mean, it's exactly what you know. Yeah. So it's the dimension of the category times the dimension of the Müger center. Why call, well, before this, so I want to present the result, but before this is a typical terminology that people use, and it's if the Müger center is Tannakian, so it's the category representation of an ordinary group as a symmetric category. This is called a modularizable braided category. If it is not, then it's called non-modularizable. In this case, the category is the representation of a supergroup, and the point is that the existence of minimal molar extensions it's going to depend directly on what is the shape of the Müger center. So the distinction between Tannakian and non-Tannakian will be crucial in order to understand the obstructions. So let me first present the solution in the modularizable case. So in order to do that, I have to remember and to say why this case is called modularizable. And this came from some result of the beginning of 2000, perhaps in 2000, if I don't, 2000 or 1999. I don't remember right now, but it is in different papers, independent papers of Alain Bourrier and Michael Müger, when they prove the following. If you have a braided category and you have a copy of the category representation of a group as a symmetric category inside of the Müger center, then you can consider inside of this category, you have a canonical algebra, the algebra of functions over a group. This is a commutative algebra inside here. So you can take modules over B. And this is called the de-equivalentization. Yeah. And this is again, in this particular case, this is again a braided category because it lives inside of the Müger center. In general, that's not the case, but here it is. And the main result is that if you have a braided category such that the Müger center is Tannakian and you apply this construction that's called modularization, then the quotient or the de-equivalentization is non-degenerate. Yeah. And what happened in the other case when the category is non-Tannakian, is super-Tannakian? Then inside of here, there is a maximal Tannakian subcategory that corresponds just to the category representations associated with the quotient. And in this case, when you apply this de-equivalentization, you obtain something that is not molar, but it's slightly degenerate or supermolar. Some people call supermolar. Yeah, yeah. So that's the two extreme cases. That's why this is called modularizable. So in the case that we have a braided ribbon structure, this category is even molar.
Can I ask
Yes.
about the definition of minimal modular extension?
Yes.
It's not always exist. But what is the point of using this definition for minimal? You can say the, the modular extension with the smallest dimension. For example, the Dreyfus center always exists. You can say.
Yeah.
What is the point to follow this equality instead of just taking one which is the minimal single dimension?
Yeah. I mean, you're right in the sense that this is a good point. If you take a braided category, always this is included in the Dreyfus center in a natural way. So for that reason, always should exist one modular category of possible minimal dimension. I agree with you. So in principle, we can have a different definition of minimal and modular extension following this. But he was interested in to know if this bound is always possible. That's why he called minimal. And then the principle, if you try to see basic examples, always you can find this. So it's not immediate to see that this is not true. I mean, it's really complicated, in fact. Yeah, but I agree with you. So
if the modular extension exists, it's the modular extension of minimal dimension. So.
Yeah, I mean, exactly. This is, I mean, if a minimal modular extension exists, it's not possible to get something smaller than that. Yeah, that's the point. But yeah, this is a good point. The point here, as I said, is that differentiation always reduces the size of the Müger center. That's in substance the point. But in the non-Tannakian case, the best that you can obtain is super big. You cannot go down. Okay, I need to introduce two things in order to describe the obstruction. One is what people call the Picard-3 group. So the Picard-3 group, it's a monoidal bicategory. And so this here is only 2 lines. I did a mistake. It's not 3 lines, it's only 2 lines. So it's a free category with one object. So it's a monoidal bicategory where objects are invertible bimodal categories. Morphisms are equivalent classes, equivalents of bimodal functors, and 2 morphisms are natural isomorphisms of bimodals. Yeah. Okay. And the point that I will use is that in general, there is a map that goes from this Picard group. Look that now it has only 1 line. That means that we are truncated this categorical group to the group of braided automorphism. This is called the alpha induction, the map that goes from here to here. But in the non-degenerate case, this is an equivalence of monoidal categories or an equivalence of 2 groups. This is something that I will need. I mean, in general, you only have a map in this direction, not in the other way around. It's a result of everything of Nietzsche and Oster in this paper of homotopy fusion categories. Oh, there is some mistake here. Why? Oh, this is not my one. I think I did a mistake in the. No. Oh. What happened? It's supposed to be another different. Maybe I did a mistake when I sent to you my presentation. Sorry. Oh, I have to use the Blackboard because it says that I did a mistake and there is no one important slide that well. I use the blackboard in this part. So, yeah, I know that in Zoom people cannot see, but okay. So now I need to define the H upper for obstruction. And the idea is the following. Oh, was my mistake. If you have a braided category, as I said, inside of this, you have the Müger center. And I am interested in the case that is the representation of a group. And then I can take here the de-equalization. The point is that this de-equalization, the group G, acts on the de-equalization. So in particular, this means that you have a group from here to the tensor automorphisms of BG. You have an action of this to this. And I said, in addition, we have that this is equivalent to the Picard group of BG. Because in this particular case, this category is not degenerate. I'm using the result of that this is modular. So a natural question, remember that I said that this is it's a monoidal bicategory. Or in other words, that people call a free group or a categorical two group. And the question is when this map, let me call this map rho tilde, when this map can be lived, if there exists a lift of this map to the whole Picard. Yeah. And this always, the existence of this is a, for the general theory of homotopy type theory, the existence of a map it's given by an element in H3 of G with coefficients in P3 of this categorical group that in this particular case corresponds to this. And I call this element O4 of G. So, given this, there is a canonical element in, here is H upper 4. In H upper 4, that is the obstruction to the lifting of this canonical map to this. Yes, and this is what we call the H upper 4 obstruction. The result, let's say the first part of the main result is that if B is a modularizable braided fusion category, then B admits a minimal molar extension if and only O4 of B it's equal to 0. And in this particular case, the set of all minimal molar extension is a torsor. It is a torsor. The set, it's a torsor where H upper 3 of G with coefficient C star. This part was already proved I mean, the part of the torsor was already proved by Liang, Kong, and Xiao Wen. And what is the point? The point now is that knowing this, for some particular cases, we can even explicitly describe the four-cause cycle. So we found explicit formulas. It doesn't matter, the formula looks very ugly, and it is, but the important point is that there is a concrete formula that you can plug in order to check if something, in some particular cases, has or not a minimal molar extension. And what we did was to apply it to, because to the example of Drinfeld, that is a very concrete example. It's to consider what people call a molar category over Z2, with an action in this particular case of this group. Then appears a very concrete four-cause cycle. We computed and we saw that this is not, the cohomology class is different to 0. And so that gives let's say, an alternative and different proof that the original proof of Drinfeld, that this is an example. And even we present another family, like an infinite family of fusion categories that does not admit a minimal molar extension. So really, this is not a real phenomenon. I mean, it appears a lot, this kind of things. And also we can, I mean, because we have explicit formula, it's relatively easy to compute. Also because this cohomology, in many cases, well, depending on the group, but if the group, for example, is abelian, there are effective computational ways to check if it is 0 or not. At least for abelian groups, it's pretty simple. Now, what happened in the other case when the category is not modularizable? In this case, we need to develop a whole theory of actions of supergroup over fusion categories, because one of the things that we need, and also we need to construct an obstruction theory for actions of supergroup on braided fusion categories. And then what we did was to propose the notion of fermionic actions. That's, we believe, what it means to have the action of a supergroup or a fusion category. And yeah, as I said, we did a complete obstruction theory, but I don't want to present that part right now. I only want to present like the main results. So let me explain a little. Well, yeah. So there is a more general notion here that works for any possible fusion category of what we call a fermion. Well, it's something that in the literature appears, especially for braided fusion categories, but this also can be defined for an arbitrary fusion category, what a fermion is. Basically, yeah. But here for the presentation, I will take only the case of braided fusion category. So we call, a braided category is called a spin braided fusion category. If first you have the braided category, but inside you have a simple object such that the square is equal to the identity object, and the braid it's basically the same as the category as the odd part in the category of supervector spaces. So really what we are saying here is that subcategory generated by the unit object and by F is a copy of supervector spaces. So when we said really a spin braided fusion category, we just mean a braided fusion category with a copy of supervector inside. That's just, yeah. And in this case, really, to talk about spin braided fusion category is exactly the same in terms of what people call enriched category theory, exactly the same as to talk about braided categories over the category of super vector spaces. Instead of working the category of vector spaces, we are now working the category of super vector spaces, but yeah, we prefer not to work in the, I mean, it's possible. My point is that it's possible to describe and to define the things in the world of enriched category theory and probably has a more natural categorical description, but we prefer to do it directly in terms of braided fusion categories and not apply this theory. And of course, the typical examples are the category of supervector spaces itself. There are many, but I want to present just two. The category of supervector spaces. The other one is in general the category of the Ising category. This plays an important role in fusion category theory, but this is a very special kind of fusion categories that is relatively small, only have 3 simple objects, and the fusion rules are pretty simple. This is the fermion, that's why I call F. So F to the squares, it's equal to the unit object. F, this sigma to the square is 1 plus F, and F sigma is equal to sigma. So yeah, this kind of fusion categories always admit a braided structure. In fact, it's a non-degenerate. In fact, it's modular. So always admit a modular structure. And this F is always a fermion. And it plays again an important role in many cases. I have already said what a finite supergroup is, but in order to define what the action of a supergroup on a spin modular category is, I need to remember a couple of things. The first is a finite supergroup. As I said, it's just a finite group with an F central element of order 2, just that. Of course, if you have a central element of order 2, you have a central exact sequence, yeah? And if you have a central exact sequence, this is up to equivalence. This corresponds to an element, in this case of H2 of G with coefficient Z2, yeah? So you can think of a supergroup in a slightly different way, as a finite group G with an element alpha in the second cohomology group. This is another way to think about that. And for example, the trivial supergroup corresponds to alpha equal to 0. And now, because I want to define the notion of what is an action of a supergroup on a spin braided fusion category, I need to define what kind of functors I will use, and we will say that a braided functor is fermionic if it respects the fermion. So you have a fermion, particular choice of a fermion here, particular choice of a fermion here. Braided functor is fermionic if the fermion here is sends to the fermion here. Yeah. Here I am using an isomorphism, but really this is not like a extra structure, it's just a property. And then now I can define what exactly a fermionic action means. That is, so you have your supergroup that I am looking at this supergroup as the following. It's a finite group with a choice of an element in H upper 2 with coefficient in Z2. Yeah, this is different. And what I mean by a fermionic action, it's an action of the group over the braided automorphisms of B that fix the fermion F. So this can be called, I don't know, the fermionic action. So this is the group that fits F. And the point is, remember that inside of B we have this fermion. So if you restrict the action of the group to the copy of supervector spaces, these kind of actions corresponds canonically with element in H upper 2. So the idea is that the restriction of G to the fermion that corresponds to an element in H upper 2, has to correspond to the alpha associated with the original supergroup. And why this is a good definition, basically for this result, that you have an equivalence of two categories between the following: spin braided fusion categories with a fermionic action of these fixed supergroups, and braided fusion category that contains the category representation of the supergroup. So it's basically the same. So that's why this is a good definition. And even I don't want to present, but one of the things that we did was study the obstruction theory. So if you have a group homomorphism from G to this group, so the abstract group of tensor automorphism of V, the natural idea is to think when this lift to a really fermionic action, and we define some cohomological obstruction associated to that. For the presentation of the obstruction theory, it is not necessarily the obstruction. So that's why I don't present. But when you really need at the end to compute examples and to see what happened, the obstruction theory is necessary. That's why we developed the paper. And now I can present the second part of the main result. So suppose that you have a braided fusion category, and now in this case, the Müger center is not Tannakian. So it's a supergroup, it's the category representation of a supergroup, so it's not modularizable. And you want to know when this B admits a minimal molar extension. In the past, it was just to see if this H upper 4, in this case of it was 0. Now it's much more complicated. So in this particular case, you have to take the decurrentization. This decurrentization is not a molar category, it's a slightly degenerate molar category. So the first problem is that you need, we know by the result of Theo and David, Johnson and Hoyta, that these always admit a minimal molar extension. So and there are exactly 16 molar extensions. So in order to know if this P admits a minimal molar extension, you have to first pick one of these 16 molar extensions that we know exist. And then we need to know if the supergroup acts fermionically. Because this is always fermionic. It's an spin molar category. So we need to know if this supergroup acts fermionically on S, on the minimal molar extension, in a compatible way. And after that, because it acts on this, we can apply the previous result because this to this category. And if the anomaly is 0, then the minimal molar extension exists. So now it's much more complicated. It goes through 3 steps. But this is, we prove that this is if and only if condition. So let me present again, especially because I did a mistake and I couldn't present in the slides the first part of the main result. So we provide necessary and sufficient conditions for the existence of a minimal molar extension as follows. In the molar case, there is this H upper 4 element, and we have formulas, at least in some particular cases, that is very general, of the obstruction. And in this case, everything is controlled just to know what happened with this particular element. Yeah. So if this element is 0, then the obstruction exists. And if it is not moralizable, you have to be more careful. But using the result of Johnson, Pride, and Hoyta, what we need is take some decurrentization. This is a slightly degenerate. Then we need to take an extension. This is the minimal molar extension that Johnson, Frey, and Reuter construct. Then we need to see the fermionic action, and then we need to check if the obstruction is zero. Of course, it's complicated. To be honest, there is a gap here. And the gap is, I still don't have a concrete example of a non-modular, of a braided fusion category non-modularizable that does not admit a minimal molar extension. This is complicated, really complicated to find a complete example of that. I believe it exists. So still, I mean, I'm working on that, trying to construct a complete example of that. It will be, because there are many steps, in particular, in general, to compute fermionic actions, depending on the kind of category, could be complicated. But in principle, theoretically, that's possible to do it. So, yeah, that's what I wanted to present. Thank you very much.
Let me start. Can you come back to the definition of modularized the same
Modularizable.
I just wanted to know what is the, so you said the modularizable means the Müger center is Tannakian.
Exactly.
Non-modularizable is super-Tannakian.
Yeah, exactly.
What's this is notation is due to Alan Müger.
Yes, exactly.
What is justified to call that modularizable? Or what he has in mind when he said that? Because
is this theorem that if the category is Tannakian, when you take the decurrentization, this is a molar. But in the other case, it is not molar, it's supermolar. That's why he called modularizable, in the other case, non-modularizable. Exactly, supermodularizable. It could be another definition exactly. Yeah. But look something that happens with this result of Theo and David. That again, this is not. I mean, this decurrentization is not molar, but always admits a minimal molar extension. So there is another fusion category, slightly bigger, of the double of the dimension, that is modularized. Yeah.
can you repeat the gap you talked about?
Oh yeah, well, it's not a gap really. It's I don't know at this moment a concrete example of a braided fusion category, non-modularizable, that does not admit a minimal molar extension.
Your if and only segment is true up to this gap, or it's
No. There is no. Perhaps that wording is not a gap. It's that I don't know a concrete example. I mean, as I said, maybe I can explain better what I mean. As I said here, I can present, or here really, I can present an infinite family of fusion categories that does not admit a minimal molar extension. In the other case, I don't have explicit example. Yeah, but the proof and everything is correct. There is no anything strange there. The point is that the computations, I mean, if you remember, there are many conditions, and these conditions in general are not easy to solve. Theories. Yeah. So first, I need to find a minimal molar extension. This is kind of constructive, but not completely. And there are 16. So in order to check this, I have to check not for 1s. I need to check for 16. And I need to find all the actions for those 16. And then I need to compute for 6. So it's much more complicated. That's my point.
So if there are 16,
yeah.
Any braided category?
Yeah, this is this is one result that in general, for a slightly degenerate or for a supermodular, there are 16 minimal modular extensions, different 16. 8 of that can be constructed using testing, and the other 8 are constructed differently.
So what is the example you are not able to find regarding this misfits of assumption?
I mean, I have very concrete example when I have been working on. Yeah. But again, the point here is that I need to find a concrete braided fusion category with Müger center that is super-Tannakian, but such that I prove that no one, I mean, that these conditions cannot be satisfied. And as I said, the point is that it's something that can be done, but it's a lot of computations. And even for the smallest case, that if the case corresponds to the Dreamfield example, the computations are not really trivial, let's say. And the typical example that I have tried, it's even bigger. So I think at some moment I really need to use the computer. That's the point. I try to do it by hand, but I think that a computer is necessary.
So they are in relation between, so you want to check your condition for all 16 of them, for the non-modularizable case. Are there any relations between this?
Yes, of course. I really, to be honest, I don't need to do it for 16 different ones. And there are some arguments, as I said, they are related to it by testing. So really, I only need to check in 2 different families. Yeah. But one of the families is constructed using one technique given by Yang, Kohn, and Xiaowen that is called like icing twist. And the dimension of the whole category changes importantly. In particular, if you start with an integral category and you apply this construction, you get something that is not integral. So it's much.
Another question. So if it's a super extended series like that, only from things to
Yeah, excellent question. Thank you. Yes, in fact, in the paper of Johnson, Friedman, and Reuter, they rewrote part of my obstruction theory in terms of super homology. So there is a reinterpretation of many of these parts in terms of homology notebook. I mean, it's some kind of special homology associated directly with the supergroup. But the point is that when you really need to compute that to know if something is zero in the group homology, at the end, what you have to do is to do part by part, and it's really what I define. Yeah. So yeah, it's equivalent, let's say. Yes.
Another question.